So, today we are going to be starting to talk about logarithms. Right? And what logarithms are is they tie together two of our previous ideas of inverses and exponential functions. Because if you remember, if I had some exponential function, right, that looks like f equals a to the x, right, where a is bigger than 1, then our graph looks something like this thing. Okay? What logarithms are, our logarithms are inverses for this thing. So if we flip all our x and y values, right, a logarithm is going to look something like this thing. Right? To where for the exponential function, remember that's the point 0, 1, which means this point becomes 1, 0. Right? So if we think about logs, they're going to be set up just like this. Right? It'll be log of my base of some value. Okay? So for instance, maybe I will have log base 7 of a variable x, or I could have log base 3 of 22. Right? If you remember, for your exponential functions, your base has to be a positive value, and it's the same thing for the logarithms. This base has to have a positive value as well. Okay? And there is a relationship between logarithms and exponential functions. So for an exponential function, we have a base raised to an exponent, and when we multiply all that stuff out, we get some type of an answer. So for instance, 2 raised to the 5th power is 32. Okay? So 2 is my base. Right? 5 there is my exponent. And the 32 is my answer. Okay? Here's how we can write this as a logarithm. We would write it as log of my base of my exponent. Right? That's going to equal, just kidding, let me erase that, of my answer. Right? That's going to equal the exponent. So this logarithm that we had a second ago, this 2 to the 5th equals 32, right? I could write that as log of my base, right, which is 2, of my answer, which is 32, equals 5, my exponent. Right? So we can go back and forth between logs and exponents by switching them around like that. Okay? So for instance, if I had, how about 7 squared equals 49? I could write this as log base 7 of 49 equals 2. Or if I go backwards, if I had log base 8 of 64 equals 2, I could write this as an exponent to where there's my base, right? So it'll be 8. There's my exponent, so it'll be 2, and that equals my answer here, which is 64. Okay? For another example here, if I had log base 3 of 81 equals 4, then I could write that as an exponent as, not an 8, but 3 to the 4th equals 81. Right? Because again, there's my base, there's the exponent, and here is my answer. All right, so that's how we can kind of go back and forth between these two. What if I gave you something that looks like this? If I said 12 squared equals 144, then how could I take this exponent and write it as a logarithm? We could say log base 12 of my answer equals the exponent. Right? It doesn't necessarily just have to be numbers. We could throw variables in here as well. what if I had something that looks like log base 2 of v equals u? Then if I wanted to write that as an exponent, that would be my base here, which is 2, raised to my exponent, which is u. That is going to equal my answer, which is v. So this exponential function corresponds to that logarithmic function. Okay? So going back and forth really isn't too bad, right? How would you rewrite this as an exponent? Log base y of x equals minus 8. Well, my base is y, my exponent is negative 8, and my answer equals x. So that's how I could write that as an exponent. Okay? Flipping it around a little bit, if I gave you 8 to the b equals a, then the way I could solve this or write it as a logarithm is log base b of a, log base 8 of a equals b. Because again, we have my base, which is 8, my answer, which is a, equals my exponent, which is b. Okay. All right. We can actually use this to help us evaluate different types of logs as well. For instance, if I had log base 6 of 216, right? What does this equal? Well, I like to write these things out as exponents. So let's say that log base 6 of 216 equals x. Right? Then as an exponent, this says 6 to the x equals 216. Right? And if you think about 6, 6 times 6 is 36. 6 times 6 times 6 equals 216. So 6 to the third equals 216, which means I could come over here and say 6 to the x equals 216, but 216 is 6 to the third. So in order to solve this, these exponents have to match up, so I know that x has to equal 3. Okay. Another one we could do looks like this. What if I had log base 2 of 64? What if I wanted to ask you what that equals? Right? Well, again, let's just set it up like this. Let's say it equals something, and we can call it x. And then I could write this as an exponent where my base is 2, my exponent is x, and that's supposed to equal 64. Right? And 64, let's see, 2 times 2 is 4, 2 times 2 times 2 is 8. If we do it 4 times, we get 16. Let's see, so 2 to the 5th is 32. 2 to the 6th equals 64. Yeah, so if I have 2 to the x equals 64, 64 is the same thing as 2 to the 6th. Right? So this exponent has to match that exponent, and the answer here is x equals 6. So I can come back up here and say log base 2 of 64, that equals 6. All right. So going back and forth between these logs and exponents really isn't too bad. One other note here for you. If I don't have a base on there, right, and I ask you to evaluate that, right, if there's nothing that's listed right there, assume that it's the number 10. Okay? So this would be the same thing as 10 to the x equals 1,000. Of course, 1,000 is, let's see, 10 times 10 is 100. So 10 times 10 times 10 is 1,000. Right? So 10 to the third equals 1,000. So 10 to the x equals 10 to the third. So x equals 3. Okay. All right. As I mentioned before, logarithms and exponentials, right, these are inverses of each other, right, which means they can undo each other. And the thing you have to be careful of here is that you want to make sure that your two bases are the same thing. For instance, if I had log base b of b raised to the x. Right? This is an exponential function with base b. This is a logarithmic function with base b. Right? Since those two bases are the same thing, these are inverses of each other. Right? So that means they just undo each other. So this should wind up just giving me an x right back. Right? So for example, if I had log base 7 of 7 to the x, since the base in the logarithm matches the base of that exponent, I just get this right back. So I just get x. Right? So log base 3 of 3 raised to the 4th power just gives me a 4. Right? Log base 7 of 7 raised to the minus 6 power just gives me a minus 6. Okay. Log base 11 of 11 squared gives me the number 2. Okay. All right, and on the flip side, for exponentials, if I had a base for my exponent, and up in the exponent spot I had a logarithm with the same base, right? So again, we have an exponent with base b, and we have a log with base b up in the exponent spot. Then again, these things are inverses of each other. Right? So if I had, how about 5 raised to the log base 5 of x? Right? We stick x into this log base 5, and then we raise that to the exponent 5. So again, they're inverses, so they undo each other, and we just have an x. Right? So if I had 3 raised to the log base 3 of x, that's just going to be x. If I had a 5 raised to the log base 5, really of anything, let's say, how about 17, that's going to return a 17. Or if I had 8 raised to the log base 8 of 4, that's going to be 4. The thing you have to make sure you're careful of here is that the base for your exponent and the base of the logarithm, they have to be the same thing. If they're not, we're stuck. We can't do anything. So if I had 3 raised to the log base 5 of 9, since this base 3 is different from that base 5, right, we can't simplify that. Right. Now, there are some cases where you might be able to manipulate it to help you out a little bit. For instance, what if I had log base 3 of 9? Well, if you rewrite 9 as 3 squared, now this base and this base are the same thing, so they will undo each other, and we get a 2. Right? So if I had log base 5 of 625, well, if you factor it, 625 is the same thing as 5 to the 3rd power, right? And those will undo each other, and I'm just left with a 3. Same idea for exponents. What if I had a 9 raised to the log base 3 of 20? Right? How can I simplify that? Well, this base and that base are 2 different values, but can we actually make them the same value? Right? Well, 9 is the same thing as 3 squared. So I'll have 3 squared raised to the log base 3 of 20. Okay? And if you remember your properties of exponents, if you have a power raised to a power like that, remember you multiply those together. Okay? So this is going to equal 3 raised to the 2 times log base 3 of 20. Okay. All right, and we'll touch on these in just a second, but for my properties of logs, I could actually take that inside my logarithm and make it 20 cubed. And now, since this base and this base are the same thing, that's going to simplify into 20 cubed. Okay. All right, so let's go over some of these quick properties of logarithms to make sure we can remember how to do them. Okay. First of all, if I have any log of x times y, I can turn that into the log of x plus the log of y. So if I had the log of 7x, that's the same thing as log of 7 plus the log of x. Right? Or the log of 28, that's the same thing as log of 2 times 14. So I could write this as log of 2 plus log of 14. Right? If I had the log of x over y, right? So there's my first property, here's the second one. We can break that apart as a log of a difference. So it's log of x minus log of y. So the log of 7 over 3, that's the same thing as the log of 7 minus the log of 3. Right? Or what about the log of x plus 1 over x minus 1? That's the log of x plus 1 minus the log of x minus 1. Okay. By the way, notice I do not have a property if it's a plus or a minus on the inside, so these are done. We can't break those apart anymore. Okay. The third property we'll talk about is, what if I had the log of x raised to the y? That's going to be the same thing as y times the log of x. Right. So if I had the log of 9 squared, that's the same thing as 2 times the log of 9. Right? Or if I had the log of x to the 5th, that's the same thing as 5 times log of x. Right? Now the thing you have to be careful of is you have to make sure that this exponent goes with everything inside your logarithm. So if I had the log of x cubed plus 1, I can't pull that 3 down front like this because that 3 is associated with the x, but the 3 is not associated with the 1. If it was the whole thing raised to the third power, like this, then I could bring that power down front and make it 3 times the log of x plus 1. Right? So again, this property is good for an entire function raised to a power, not an individual term raised to a power. So if I gave you this, how about the log of x squared times y to the third? And I wanted to break it apart. What I can do first of all is recognize it's a multiplication problem like that. So I can break it up as the log of x squared plus the log of y cubed. And then I can use that last property to bring that exponent down and make it 2 times the log of x plus 3 times the log of y. Right? If I had the log of a times b times c, I could think about it like this. I can make it the log of a times b times c, and then that becomes the log of a plus the log of b times c, and then I can break that second one apart again to make it the log of b plus the log of c. Okay. What if I had this logarithm? Log of the square root of x times y times z. Okay. Well, if you remember your properties of square roots, that's the same thing as the 1/2 power. So the first thing I can do is I can pull that 1/2 down, and then this becomes the log of x times y times z, which I can then break that apart as the log of x plus the log of y plus the log of z. So we've got these three things there. Don't forget to distribute that 1/2 through all of them. We can, of course, also work backwards here. What if I gave you log base 3 of u minus 5 times log base 3 of v? let's look at this part first. I could take that 5 and I could move it back inside my logarithm and make that a v to the 5th. And now, since both of these have the same base, I can combine them together. Right? And remember, if I have two things subtracted from one another, that turns into a division problem inside my log. Right? So it'll be u over v to the 5th. Okay? What if I had this example? What about 4 times log base 7 of u minus 20 times log base 7 of v? Okay. Well, let's take those exponents inside first, so that'll be a u to the 4th, and this will be a log base 7 of v to the 20th, and then since this is a subtraction problem and they have the same base, I can combine them together into one log base 7, where it's this first term, u to the 4th, over the second term, v to the 20th. Right? And now we've combined them together into a single log. All right, so lastly, let's think how we might be able to start solving some of these things. For instance, what if I gave you this? What if I said log of 10 minus 4x equals log of 10 minus 3x? All right, for starters, if I don't give you a number for the base, remember we can assume that it's log base 10. Okay? So what I need to do is I need to somehow get this x term and that x term out of the logarithm. Right? So then the question would be, what's the inverse for the log? Right? And if you remember, that's an exponential function. So since the base we're using here is 10, what I'll do is I will take the left-hand side and make it the exponent for 10. And what you do to the left-hand side, you have to do to the right-hand side. So that'll be a 10 raised to the log base 10 of 10 minus 3x. Right? So now I have an exponential function with a base of 10 and a logarithmic function in the exponent spot with a base of 10 here and here, which means they're inverses of each other. So those are going to undo each other, and I'm left with 10 minus 4x over here. And on this side, I've got 10 minus 3x. Right? I could subtract 10 from both sides. Maybe add 4x to both sides, and you get your solution there. X equals 0. Okay? Let's try another one. What if I had, I don't know what that is. What if I had negative 2 times log base 5 of 7x equals 2? Okay. Well, for this one, why don't we go ahead and divide both sides by a negative 2? And then I'll be left with log base 5 of 7x equals 1. Right? Since we have one logarithm, why don't I try to rewrite this as an exponent? See if that helps out. Okay? So there's my base, there's my exponent, and that equals this, which is my answer. And now I can divide both sides by 7 to get x equals 5 over 7. Okay? So when we had those two exponents in there, we had to find a way to, or I'm sorry, those two logarithms in the previous example, we had to get rid of both of them. Here, if you just have one, isolate it, rewrite it as an exponent, and see if that helps out. Okay? All right, here's one more for you. What if I had negative 6 times log base 3 of x minus 3 equals negative 24? Okay? Let's isolate that logarithm. So let's divide by a negative 6, and that'll give me log base 3 of x minus 3 equals 4. Right? Now I can rewrite this as an exponent. There's my base, there's my exponent, and that equals this answer. Right? Now 3 to the 4th, that's 3 times 3 times 3 times 3. Right? That gives me a 9, that gives me a 9, and then 9 times 9 is 81. So I have 81 equals x minus 3, and if we add 3 to both sides, I get x equals 84. All right, so we'll have a whole bunch of these things that we are going to work on in class. So I will see you then. Hope you guys have a spectacular day.